So those homeworks due Friday, test, in this case due Sunday, I moved that back. I don't think I need to mention anything else. So today what we're gonna do is we're gonna start in section 2.3. And we're actually going to use the book a little bit more today, just for the sake of not having to write all the word problems down. Okay, so that's the idea. So we'll look at the book, but I guess before we do, two, three is on linear models. It's linear equations and models. And basically the goal is we are going to make a linear equation from some word problem. Okay? So the goal in most of these is to make a linear equation. All right? And like I said, usually it's from the context of a word problem. And the nice thing is that we've made linear equations before. Remember when we were given slope and given a point, we can create a linear equation, find the slope, find the b value, we got the linear equation, right? So it's just like creating the y equals mx plus b that we've dealt with before. Right? So we're going to find the slope using whatever tools we have. In section 2.1 and 2.2, we found the slope. Well, one way we found the slope was when the slope was given to us. Another way we found the slope is if we have 2 points, we can calculate slope by y2 minus y1 over x2 minus x1. Another way we can find slope is if we know a line is parallel, they have the same slope. Another way we can find slope is we know if the line is perpendicular, the slope is a negative reciprocal. Everyone remember those things? So, same kind of thing. So find the m, find the b. We always find the b by plugging in a value into x and y after we found the m, right? And then write the equation. So the goal is to create a linear equation, and we do it in the same way we've been doing it. Now it's just in the context of a word problem. And then once we have that linear equation, we can use it. We can say, well, once we know the linear equation, if I plug in a certain x value, what's the y value that we get out? If I plug in a certain y value, what's the x value have to be? That makes sense. So then you can plug in numbers into that equation and find other points. So goal is to create the linear equation, and then we use that linear equation. Now, in this section, since we're dealing with linear models, we're going to assume linear growth a lot. But I want to put the caveat out there that not every real world situation is a linear growth situation, okay? And we will see that as we move on in the semester. There's other models, like exponential models, that we're going to look at in later chapters. So just because this chapter gives us a lot of linear growth, don't assume that every single thing is going to give us linear growth. For instance, oh shoot. Again, let's take a look here into our book. We'll pull off. Uh-oh. Hit the wrong one. Agree. That's weird. Logged me out or something. I don't know what happened there. There we go. There's some problems. Good. So I'm going to highlight this one. Just so I don't have to write it. This is a problem in our book. I'll write the basics of it on the board. And then we'll solve it. So we're going to consider this scenario. A town's population has been increasing at a constant rate. In 2010, the population was 46,020. By 2012, the population had increased to 52,070. So we're assuming constant growth rate, constant increase. In 2010, the population was 46,020. In 2012, the population was 52,700. Now, we'll eventually get to problems 11 and 12. But before we do, we need to create the linear model. All right. Now, here's the deal. Let me. If we assume it's constant rate of growth, that's basically indicating that we have a linear growth. All right. Usually population is not linear growth, but we're assuming in this one it is. what we're given here is essentially 2 points. Now, sometimes we're going to let our time start at time 0. And other times we'll let our time start at a certain year. Okay. When you go onto Moodle, it'll explicitly state which year to start at. So let's assume a time, we'll call it time t equals 0, means the year 2000. Is that okay? If time 0 means 2000, then what we have here is essentially 2 points. One of which is coming from the fact that the population in 2010 was 46,020. And the other would be 125270. Now, if you let your 0, your time of 0, be some other year, let's say we made our time 0 2010, then this one would have been 0 46,020, and this one would have been 2 52,007. Is that okay? So be careful about where time 0 is at. Now, we want to create a linear model. We want to create what the population is at a certain time period. I'll call P, capital P, the population. That's going to be my sort of output value. So instead of using X's and Y's, I'm going to use population. I'll use P for population, and I'll use T for time as my X. Okay. It's the same exact thing we've been doing, just using different letters instead of X's and Y's. Is that right? First thing we want to do is create the slope. Since I'm given 2 points, I can find the slope by y2 minus y1 over x2 minus x1. Excuse me. And I get a slope of 6,050. That's a positive 6,050. By the way, in the context of this problem, that would mean we are increasing by about 6,050 people every single year. Right, the town's population is increasing by that many every single year. Oh, I'm sorry, no. I misspoke. That was the line before. Should be 3,025. My apologies. 3,025. I looked at the wrong line on my calculator there. One where I'm not divided by 2 yet. So Okay, sorry, so let me rephrase that. So this 3,025 means that the town's population is growing by about 3,025 people every single year. Now that we have that, we plug it into our model. Our population is going to be 3,025 times T plus some B. Now I plug in one of the points. It doesn't matter which one. I'll plug in this first one, I guess. 46. 20 equals 3,025 times 10 plus B. 3,025 times 10 is 30,250. And if I subtract that 30,250 from both sides, and I'm writing low, can't see that. Back. We end up getting 16. Oh no, shoot. 15. Sorry, I should do this on my calculator. Speed over or something. Okay. 15. 770. That's my value. Everybody else got pretty good with that number. All right. So my equation, my linear equation is that the population is going to be 3025 multiplied times your time plus 15,770. Now, again, I'll emphasize that's the equation when we assume time 0 means 2000. If we assume time 0 means 2010, that equation would have been slightly different. And that's the main part. The main part is, can we see that these two pieces of information are really points, two different points of a line? Once we see that these two pieces of information are essentially giving me points on a line, then I can create that line. And then I can answer questions like the book asks. For instance, predict the population in 2016. And then identify the year in which the population will reach 75,000. All right. So if I'm going to predict the population in 2016, I go back and I say, well, T of 0 means 2000. So 2016 is a T of 16. So I plug in that 16 into my equation. This is just calculator work. And I get 64,170. So the population in 2016 will be that number. 64,170. According to this model, obviously. So I'm just plugging in for T, finding the P. The other question, when will the population be 75,000? Well, that's just plugging in 75,000 in for the population and then solving for T. So you can subtract 15,770 from both sides. $75,000 minus 15,770 gives you 59,230. Divide both sides by 3,025. And I got about 19.58. So T is about 19.58. What that means is that sometime in the year 2019, probably about 0.58 into the year, the population will turn 75,000. Will hit 75,000. So sometime in the year 2019, basically, in the back half of that year. Any questions about that? Like I said, the main part is, can we create the equation? And then we can answer questions once we have that equation by, in this section, all the questions that I'd ask are to plug in a certain value for the X part, what do you get for your Y? Plug in a certain value for your Y part, what do you get for the X? Does that make sense? Let's do another example. So this one is baby's weight. So the weight of a newborn is 7.5 pounds. the baby gained 1/2 pound a month for its first year. So gained 1/2 pound a month. All right. So this says find the linear function that models the baby's weight. We'll call that W. As a function of the baby's age in month, we'll call that T. All right. So W is weight and T is time in months after the baby's born. Model for weight where T time is months after birth. Okay. All right, what we have here, again, we're trying to create a model. And it's always going to look like sort of a y equals mx plus b scenario. Or I can always think of it that way if it's linear. And I just change the letters to whatever the problem calls for. So this calls for weight T months after birth. As always, I want to start out finding the slope. In this case, gaining 0.5 pounds per month, that's the rate of increase, right? So that is the slope. And since it's a gain, it's a positive 0.5 or half. So that's given to me. The weight of the newborn being 7.5 pounds at the time of birth, that essentially tells me that I have the 0.0, 7.5, right? At time of birth is time 0, and we know the weight is 7.5. Now, if you want, you can just recognize that that's the y-intercept, or in this case, the, I guess, w-intercept. And so 7.5 is your b. Or if you wanted to, you can just plug it in. And you see that you get a b of 7.5. So the equation in this case trying to get this one, is that W is equal to 0.5 T plus 7.5. And then we can move on. Now, obviously, there's lots of questions we can ask. One of the questions that the book asks immediately is, what's a reasonable expectation for this, right? And because in the original problem it said for the first year, a reasonable domain would be, since T is in months, from 0 to 12, because that's 1 year, right? 12 months is a year. So a reasonable domain is from 0 to 12. Because it said this is the pattern for the first year, or for the first 12 months. I'm not gonna ask you domain questions too much. I'm gonna ask you more questions like, what is the weight of this baby after 4 months? Okay? Or when will this baby be 10 pounds? Yeah, let's do 11 pounds. Why not? Instead of 10. 10 is too close to 4 months. So what's the weight after 4 months? We simply plug in a 4. So after 4 months, the weight is 9.5 pounds. When will the baby be 11 pounds? That's where we plug in the 11 into the weight. Solve for T. Subtract 7.5 from both sides. And then divide by 0.5. And we get a T of 7. So when will the baby be 11 pounds? Well, after 7 months. T was in months. Is that right? So it's problems like that that are gonna come up over and over and over, all right? And the trickiest part is honestly like where to start your T at sometimes, and how to write certain, which numbers to use, basically. All right. A lot of this is money, so I don't want to do that. Yeah, okay. Let's look at number 47. Number 47 says a phone company has monthly cellular plan where a customer pays a flat monthly fee and then a certain amount of money per minute used for voice and video calling. If the customer uses 410 minutes, the cost is $71.50. If a customer uses 720 minutes, the cost is $118. Find a linear equation where we're looking for the monthly cost as a function of the number of minutes used, and we'll use X as the number of minutes used. So Y is the monthly cost, X is the number of minutes used. And it says if a customer uses 410 minutes, the cost was $71.50. If the customer used 720 minutes, the cost was $118. All right, and then what's cost after 687 minutes are used? So this one tells me the X and the Y, use X and Y, excuse me, as my variables. So I'll do that. Pretty straightforward in terms of what we're given here. If X and Y are my variables, then those two sentences where it relates number of minutes used to the total cost of the plan, those two sentences are giving me a point, an ordered pair, an XY pair. So I get 2 points, one of which is 410, comma 71.50. The other is 720, comma 118. We're trying to create the equation y equals mx plus b. So I always want to start by finding my slope. Difference in the y values, y2 minus y1, divided by difference in the x values, x2 minus x1. $118 minus $71.50 is 46.5. $720 minus 410 is 310. When I divide that, I get a 0.15 as my slope. Okay. That tells me the equation of the line is y equals 0.15 times x plus b. Now I can plug in either of those 2 points to find my b. I'll use the second point. Be careful that you plug in the 720 into your x and the 118 into the b. So I get 118 is equal to 108 plus b. Subtracting 108 from both sides. Gives a b of 10. So my equation is y equals 0.15x plus 10. So if I was to describe that plan would be, it costs $10 a month plus 15 cents a minute. So flat rate of $10 plus an extra 15 cents a minute. Okay. Now the book asks, after we found the equation, what is the monthly cost if a customer uses 687 minutes? Well, X stands for the number of minutes. So all we have to do is plug in 687 into that linear equation. And the total cost after we do that, the y value is 113.05. So $113.05. All right. Not too crazy. Not too crazy. So it's basically a lot of what we've been doing before, finding the equation. Now sometimes our x's and y's just become new letters. And then we have to sort of glean from the word problem what the 2 points are. And to give you lots and lots of examples of this, I want to just highlight number 50 here. This is about owl population. Notice that it says let the input be years since 1990. All right, that means a t of 0 is 1990. So what would a T of what would 2013 mean in terms of a T? 13, right? 2003 would be a 13. And 2007 would be a 17 in that scenario, okay? So when you're making your points, most times when you're given a task to create an equation, they'll tell you where the sort of starting year is. In this case, it was 1990, all right? In this case, notice T is the number of years since 2010. So 2010 was time of 0. All right. And then 2015 would be time of 5. So just be really careful about that kind of thing. T is the number of years since now. All right. I don't know why now, that's weird phrasing. So I just wanted to point that out, okay? And let me really quickly take a look at the homework. Constant rate of growth. Here you go, retail and markup, all that stuff. Okay, here we go. That's the one I want. On this one, this is the percentage of female cigarette smokers in the United States. It was 21.0% in 2000, and then 18% in 2006. Find a linear model where T is the year since 2000. So T of 0 is 2000, right? When you're creating this, your output could either be written as percentages or your output could be written as proportions. This one says write your output as percentages. Does that make sense? So relating the percentage of female smokers to the years since 2000. So when you think of a point, 21% in 2000, that's an ordered pair. 2000 is times 0, right? So it'd be 0, comma, 21. Everybody okay with that? Not 0, comma, 0.21. So make sure that if you're using a percentage, you use the actual percent of 21 and not the decimal version of 0.21. That's all I'm saying. Okay. So that's another little thing you can run across is sometimes, especially if our output is a percent, sometimes they'll ask for the output in percentage form, and other times they may ask for the output as decimal form. So this one's asking it for percentage form. So 21% is 21. Is that okay? All right. So I wanted to point that out because some people will struggle with that. Other than that, it's just simply recognizing context. and figuring out what's your X, what's your Y, or what's your, whichever letters you're using. Okay. Now the last section we're going to go over is linear regression. So the basics of it are, we are going to be given a lot of points. So we're going to be given a lot of points. Let me draw what I mean. Something like that. Now, these have the pattern of the line, but they are not in a perfect, they're not in perfect alignment. Okay. So first off, we have to ask, is the pattern aligned? Hopefully it is. And then we're going to create the line that best fits the data points. So we're going to let data, we're going to create the best line that best fits these data points. And like I said, since all of these points are not in alignment, your line will probably not go through and touch every single point on the graph. It's going to do something like this. It's going to be the line of best fit. Now, the natural question is, how do we tell whether that line is a pretty good fit? Like this one's pretty good. It's not perfect. There's some little pieces of error, right? Error is how far each point is from the line where it should be. So how do we tell the best fit? Or how do we tell if it's a good fit or a bad fit? So we are going to determine the fit using what's called Pearson correlation coefficient. A correlation coefficient tells us how well something fits. Pearson, that's just the last name of a person, mathematician. And a Pearson correlation coefficient is the correlation coefficient of a straight line. Okay. It's always going to be between, write that down. -1 and +1. The closer, the negative positive just means slope increasing or slope decreasing, okay? The closer it is to 1 and the closer it is to -1, the better the fit. If R is equal to 1, that means every single point is exactly on the line. All right. So closer to 1, I'll put an absolute value. Then the line is a good fit to the data. If R is close to 0, then the line is a bad fit to the data. Is that all right? So if R is close to 1, then the line is going to be a good fit. R is close to 0, then the line is going to be a bad fit. Now, there's different versions of cutoff places depending on what context we're in. So is 0.6 closer to 1 or closer to 0? Is 0.7 close to 1 or close to 0? Is 0.3 close to 1 or close to 0, right? Depending on the context, 0.3 could be either close or far away, depending on the context. In social sciences, usually they allow for R's to be pretty low and still say, yes, things are correlated. Like an R of 0.3 with a really large data set is a good correlation in social sciences. Okay. But an R of 0.3, if we have a small data set, probably is not a great correlation. Not a good fit. Does that make sense? So it kind of depends on the context, kind of depends on, you know, if you're dealing with really big data sets or not. So what are we gonna, so that's really ambiguous, right? Really subjective. So I want to state that in different contexts, in different scenarios, you're gonna have different R cutoff values. For our class, let's just use, since our class deals with pretty low numbers, pretty small data sets, let's just say this, for our class, if the R is at or above 0.75, then we'll say that the line is a good fit. If R is below 0.75, then we'll say it's a bad fit. And by the way, when I say above or below, I mean in absolute value. So ignore the negative. So for this class and this class alone, we use 0.75 as our cutoff. Now, as far as the mathematics behind this, it's going to be fairly straightforward. Well, let me rephrase that. If you had to do this by hand, all right, There are big, long formulas to come up with the line that best fits the data. It's called the least squares regression line, which we'll get into. And there's big, long formulas to calculate the correlation coefficient. But in reality, nobody does this by hand, all right? So the way I will show you how this is done, and I'll just show you a couple of examples, is I'll show you that technology gives the line best fit. The line of best fit, like I said, is called the least squares regression line. And it'll also give the Pearson correlation coefficient. We'll use Excel in this class, and I'll show you kind of how that's done using Excel. On the homework or on the test, I will have this already calculated. So you're not going to have to use Excel on the test or on the homework, but I will show you how it's done using Excel, if that makes sense. So technology is going to give those things. You could calculate them. Again, they're big, long, messy formulas. But it's not worth our time to memorize those things. You could look those up if you want. And most, even stats people, which this comes from statistics, most stats people don't memorize those formulas either. So let me show you how to do that in Excel. Do we have? There we go. Oh, sorry. There we go. So here's like a plot of points. That's not a perfect line, but we can make a line go through it. Okay. Here's a bunch of raw data where they look at the chirps versus the temperature outside. This is just how often a bird chirps compared to the temperature of the outside temperature, right? So let me go through this one. We'll create a scatter plot, see if there's any sort of relationship, if it looks like there's a relationship or not. And then I'll show you how to create the line of best fit using Excel. Again, most of this work is going to be done already for you when you look at the homework, and I'll show you that. So here's what I'm going to do. We have chirps and temperature. So we go 44, 35, 20.4. Everybody see what I'm doing? I'm just putting in the data. And right now I'm putting in all of the chirps, and then I'll put in the corresponding temperatures in just a second. All right, so I put in all of our data. And let me make this look a little bit better so you can see it a little bit easy. Let's make that 16, 18. Okay. So each one of these is giving us an ordered pair like X comma Y. Right? So each one of those is an ordered pair, and therefore it can be plotted as a point on a Cartesian coordinate plane on the XY axis grid. By the way, if you want to do that using Excel, what you do is you insert a chart, and it's called a scatter plot. Okay. So here is a plot of points on the Cartesian coordinate plane. Everybody see that? A plot of specifically those points, where the x-axis is number of chirps and the y-axis is the number of the temperature. Okay. Now you can see that really before 15 on the x-axis, it doesn't give any points, and below 40. So if you wanted to change the axis, there are ways to do it. Where we go here? Oh, 4 minutes. There's also ways to change like the design, you can make it fancier looking, right? Whatever you want it to look like. Okay. I always forget. So, oh, more options. There we go. So if you wanted to change the bounds, for instance, I could start changing the bounds. Where's the other bounds? Yeah, I'll just leave it like that. Is that okay? Again, there's different ways to play with it. I've forgotten a lot of them now. But here's what you do. You say, I want to figure out the trend line. So the least squares regression line is called the trend line. And the best way is just to go more options and say, I want a linear trend line, just a line. And then if you say, let's display the equation, it'll give you the line of best fit. And if you ask to display the R squared, it'll tell you the square of the Pearson correlation coefficient. Okay, you might ask, why did you get the square of the Pearson correlation coefficient instead of just the R? That's a feature of Excel. Because so remember, Pearson correlation coefficient only works with lines. if I would have checked one of the other types of regression, R squared is always available for those, but it's not Pearson correlation coefficient anymore. It's not a line. So they just do that. So you can see that the trend line is y equals 1.1432x plus 30.281. And the R squared is 0.9043. So in my chirps per temperature data, I got y equals 1.143. I'll round that to 2 decimal places. They rounded it to 4. I'll go out to 2. We're writing this on the board. I just take the square root of 0.9043, I'll get the R. So that's the line of best fit, which is also called the least squares regression line. The Pearson correlation coefficient is going to be the square root of 0.9043, which is 0.9509 roughly. By the way, is that that mean we have a good fit? Is our line a good fit or a bad fit to the data? Well, 0.95 is bigger than 0.75. So for this class, we're calling that a good fit. There might be a scenario somewhere out there where that's not good enough. But for our class, that's a good fit. So that technology usually gives us those two things. Once we're given those two things, then we can say, well, yeah, the data fits the line pretty well, or the line fits the data pretty well. All right. And if you wanted to predict the temperature, if you hear let's say 46 chirps. I think this was like per minute or something like that. Is that right? I can't remember. Per hour, I can't, per something, per some time unit. So predict the temperature, if I hear 46 chirps, I simply plug in 46 into my X. I do the same thing we've been doing this whole time. I got 82.72, that would be degrees Fahrenheit. As the temperature we predict. Okay. And if I say predict the number of chirps if the temperature is 70 degrees Fahrenheit, well, then we plug in a 70 for my Y and solve for X. standard solving. Subtract 30.28. $39.72 equals 1.14 times x. Divide by 1.14. $34.82. 84. 34.84. So 34.84 chirps. And again, per whatever time unit that was. Does this make sense? Again, a lot of things, this will be provided for you. All right, this equation, I'll say, hey, Excel came up with this equation with this R value. And you'll have to decide, well, is that a good fit or a bad fit based on the R value? Remember, if it says the R is negative 0.95, that would still be a good fit, right? The positive negative just means, is the slope of the line going up or down, right? The positive negative R just is an indicator of the slope being positive or the slope being negative on your line. So let me show you what I mean by that. Okay. So if you have a scatter plot and you look at a scatter plot like this, it's going to say, what's the R value? Well, if it kind of looks like a line, but it's not a perfect line would be 1 or -1, right? A really bad fit would mean there'd be scattered plot, there'd be dots all over the place. Okay. So things that are close to 0 would be dots like all over the place. So this is not obviously a perfect line, so it's not going to be 1, it's not going to be -1. It does kind of look like as you go left to right, the points go up, so it's probably going to be positive. See where I'm kind of getting with this? Trying to build some intuition. So this is probably positive. It's probably above 0.75 because there does look like there's a trend there. But it's not exactly 1. Okay. When you look at this looks like almost in a straight line, right? Almost perfectly straight, but negative slope. So the R would be negative and almost -1, right? Or maybe exactly -1, I don't know. It's perfect. After you think about how the scatter plots work, then you can see what we do. We say, here's the model that technology gave us. P equals 125.81 times T plus 19,067.45 with an R of 0.97, and then you answer questions based off of that. Okay. in the same way we just did here, right? Whether it's a good fit, whether it's a bad fit, predict the temperature with this many chirps, predict the chirps with this temperature, that kind of stuff. Okay. And those are the types of questions that I'm gonna ask. Okay, here's the model. Is that R mean it's a good fit or a bad fit? And then do some predictions. Now, even if the model is a bad fit, so let's say I have a model that is y equals 12.75x minus 13.1. And it has an R value of 0.3207. So here's the type of question. It's going to say, is this a good good fit or a bad fit? It's going to say something like predict y when x is equal to 38. And then we're going to say predict x when y is equal to 107. Everybody okay with that? So based on our R values, is this a good fit or a bad fit? Bad fit, right? It's under 0.75 in absolute value. So this is a bad fit. And here's my only point. Even if this line is a bad fit to the data, go ahead and make our predictions in this class. All right? Even though it's a bad fit, go ahead and make those predictions for the sake of, plugging things in Moodle. In reality, if you knew our line was a bad fit to the data, you probably would not use it, right? As a normal human being or as a math person, you'd say, well, our line doesn't fit the wet data well, so not going to be a useful thing to predict with. However, in Moodle, go ahead and do the prediction even though our line is no good. So we get a Y value of 471.4. And then predicting X when Y is 170. Again, go ahead and do that. Add 13.1 to both sides. 183.1 is equal to 12.75x. Divide both sides by 12.75. And I get roughly 14.36. that right? So if you are using this model, go ahead and use it, or if Moodle asks you, if the test asks you to use the model, go ahead and use it, even though we probably wouldn't in real life. Okay. Because in real life, if it's a bad fit, it means it's kind of not a very useful model. Any questions about linear regression? So we come up with this scatter plot, just a bunch of plots of points. You can kind of see if there's a trend or not. By the way, sometimes there's a trend, sometimes there is a trend, but it's not linear. Sometimes there might be a trend and it looks like a parabola, like a quadratic equation. Sometimes there might be a trend and it might look like an exponential. And you can do regression with quadratic functions. You can do regression with exponential functions. You can do regression with a lot of other functions too. Okay? But since we've been dealing with linear functions, that's why 2.4 deals with linear regression. Okay. But a lot of it's very, very similar. Just look at the model, see if there's a pattern. If there is a pattern, we say, oh, it's a line. Let's have technology build that line for us. And along with it, we'll ask it for the Pearson correlation coefficient. By the way, I showed you one way on Excel to get the Pearson correlation coefficient. That was through the trend line on the graph. But also, if you now I forget what it is. If you just write Pearson and then highlight your X values, and then hit a comma, and then highlight your Y values, notice that we get the exact same thing, 0.95, 0.9509 which is in fact the square root of that number, right? Which is what we saw. So you can get it by asking Excel for the Pearson correlation coefficient explicitly. And that's just Pearson. You highlight your X's, you highlight your Y's. And just so you know, it actually doesn't matter which way you highlight first. If you call temperature your X's accidentally and it chirps your Y's, you would get a very different looking line because you have to switch the roles of X and Y. But the amount of the Pearson correlation coefficient is the same, regardless of which one you call the X, which one you call the Y, right? You have to switch the X and Y values. Any questions about that? So Excel can give you the Pearson correlation coefficient, that's all, in a straightforward manner. All right. Well then, I know that those were the things I wanted to cover today. Like I said, I knew that it was going to be a quick day because there's not a whole lot in 2.3 that we haven't done so far. And then 2.4 is just saying, if we have a scatter plot of data, we can fit a line and do all that. So let me talk briefly about the test, and then we'll be out a little bit early. So like I said a bunch of times, test requires the Respondus browser, so make sure you download that. Okay, that's in these links here and here, tells you about Respondus. One thing about Respondus, like I've mentioned this to you guys a couple of times, but I'll mention it again. You can use your notes, your handwritten notes from this class while you take the test. However, you can't use other people, you can't use other technologies. You can't be on your cell phone when you're doing the test, okay? You can use your calculator, it's fine to use your TIA-4 and any notes you have. Respondus, when it actually first opens up, may give you some guidelines, and a lot of times in those guidelines, it'll say, make sure you don't have any papers on the table or anything like that. It's fine to have your notes on the table, okay? So you can just ignore that if it says so. The test is due Sunday at 5 right now because we ran a little bit late. I moved that back from Friday. You get 2 attempts, and each time you take it, it's timed. It's timed at 4 hours just so that people don't leave, but it shouldn't take you 4 hours. It'll take you like an hour or an hour and a half probably. Okay, hour to an hour and a half for most people. Each attempt will be different though. So it'll have different numbers, maybe a different scenario if it's a word problem like we've been doing. One of them may be population and the other may be birth weight, you know, something like that. And if you start it at like 4:50 on Sunday, it's going to automatically shut you off at 5 o'clock. Does that make sense? So make sure you're done by 5 o'clock and not still taking it at 5 o'clock. Any questions? Pretty straightforward. Yeah, so all these tests will be randomized to some degree. All right. If you don't have any questions, I'll stop there.